9 last week, and we're going to finish chapter 9 today. And we're going to use Wednesday and Friday for chapter 10. So let's get started. This is 1 and 2 sample estimation problem. I'm actually calling this final because we started last week. So what is going to be the focus today? You know, last week we focused on mean. We focus on one population, where I walk you through how to construct a confidence interval for mean, you know, when we're dealing with a large sample and when we're dealing with a small sample. And I also walk you through how to construct a confidence interval for prediction as well. But you know what, today we're actually going to be visiting two groups. Okay, I'm going to walk you through how do we construct confidence interval for difference of means. When I talk about means, two populations are involved. Then how do we compare two means that are matched pairs? Then how do we also construct confidence interval for proportion for one population and for difference of proportions when two populations are involved? And of course, lastly, I'm going to walk you through the method of estimation that I call the method of maximum likelihood. Okay, match pairs. Then how do we also construct confidence interval for proportion for one population and for difference of proportions when two populations are involved? And of course, lastly, I'm going to walk you through the method of estimation that I call the method of maximum likelihood. Okay, now I need you to pay attention. Do you know that the moment you understand what we did last week, this is just going to be an extension if you know how to construct confidence interval for mean in one population. We're actually going to extend that idea to two populations. Now, but we got conditions, just like last week, we also had condition when the population variance is known, okay, and when the population variance is unknown, okay, and when the sample size is small. Of course, we specify different formula for confidence interval. We're also going to do the same when two populations are involved. Two populations are involved. Maybe I actually want to compare the standard of living in two states. In the United States, maybe the standard of living, I'm trying to look at the average house, for instance. Maybe I'm trying to see if there's a significant difference between average annual average household income in the state of Minnesota and the state of Wisconsin. Two states are involved. That means two populations, two groups are involved, and they are independent. Okay, now what I just need to do is I need to ask myself, if I want to construct a confidence interval for the difference, I need to ask myself, do I have the knowledge of the population variance for Minnesota? Do I have the knowledge for population variance for Wisconsin? Okay, this is what I mean here. Okay, when sigma 1 square and sigma 2 square known, okay, and I want to construct a confidence interval for difference of means, this is going to be the formula. This is going to be the formula. You can say in this formula now, you can see Z, right? Now, if this is difference of means, then the whole of the square roots is the standard error for difference of means. If I multiply the whole of the square root by Z, then I have margin of error. Margin of error for difference of means. Does that make sense? Now, you can say sigma 1 squared, sigma 2 squared. We normally specify that. when the population variance are given. Okay, is there any question about this formula now? Is there any question about the formula? Okay, so if there's no question about the formula, I'm actually going to walk you through an example of this. Let's take a look at it. A study was conducted, okay, in which two types of engines, A and B, were compared. Okay, gas mileage in miles per gallon was measured. 50 experiments were conducted using engine type A, okay, and 75 experiments were done, with the engine type B. Okay, the gasoline use and other conditions were held constant. The average gas mileage was 36 miles per gallon for engine A and 42 miles per gallon for engine B. Now you are asked to find a 96% confidence interval on mu A minus mu B. Okay, I need you to pay attention to that. Okay, they needed to find the confidence interval for that. And the question now, and they said, assuming the population standard deviations are 6 and 8 for engines A and B respectively. When you take a look at this question now, they've given you population variances. Does that make sense? Now, if they give you population variances, and you can actually use, if you want to construct your confidence interval, you can use the formula here. Because this formula is actually used for constructing confidence interval for different submeans when the two population variances are given. Okay, but let me tell you this. What if in a situation where the two population variances are not given? If they are not given, we can, and then the sample that we choose from each population is large, and how large is large, at least story, we can still use this. I'm going to say that again, because I told you the other time, when population distribution is normal, irrespective of the sample size we choose from the population, the sampling distribution is also going to be normal. But when the population distribution is not normal, automatically sampling distribution will not also be normal. But do you know I can make sampling distribution to be normal, even though the population distribution is not normal? Then the central limit theorem puts that we should take a large sample size. And how large is a large? At least story. So what I'm trying to talk about, even though the population variances are not given, but the sample size is at least story, it has to be at least story from the first population, at least story from the second population, then the sample variances will replace the population variances. Does that make sense to everyone? Now, in this now, all you just need to do, you need to start you need to first start from the estimate, the point estimate of the difference. Take a look at this. If you take a look at this, we're looking at the difference, right? The difference of mean, right? Now you're going to start with a point. This is what we call the point estimate of the difference. A point estimate of the difference. We only give a single result. Now they're giving you the different. When you do that, that gives you 6. That very 6 could be wrong or right. The probability that it can be wrong or right is the same. And that is the reason why we needed to incorporate a margin of error, why we needed to construct a confidence interval. When you construct a confidence interval, we're actually going to have some belief that the true difference will lie in the interval. Now I've plugged in the values now, and I check for the 2.05 is actually, I got that from table. How? Because they say 96%. When they say 96%, what is the level of significance alpha? That will be 4%, right? Now, we should be 0.04, okay? Because confidence interval is, you are considering error at both sides. That make it two-sided. I'm going to do alpha divided by 2. I'm going to do 0.04 divided by 2. And that was why you have a z is 0.02. So I'm going to go to the Z table now, okay? And I'm going to check the corresponding values of Z score for 0.02. That'll give me 2.05. And you know what? At the end of the day, this is what I'm going to have. Now, what that guy implies right now. This guy implies the true difference of means will lie between 3.43 and 8.57, okay, with 96% confidence. Is there any question on this? Is there any question? Okay, gotta keep going now. Now, we want to consider a different scenario now. Why do I need to pull my variance? The idea of a pulling the variance will come in a situation where the population variances are not given, but they are assumed to be equal. I needed to take note of that. We normally use the pool variance approach. Okay, the pool variance approach in constructing confidence interval for difference of means in a situation where we're told the population variances are unknown, they are not given, and they are assumed to be equal. Even though they are not given, they are assumed to be equal. I'm actually going to use the idea of a pool variance. Now, take a look at this now. SP squared is what we call pooled variance. And what do you have in the formula? You have a sample variances, right? Okay, in the formula. And the idea of a t distribution is going to work here. I'll quickly take you to take a look at this. Do you see the confidence interval now? The formula has changed drastically. What do you see here? This SP now is the square root of the pool variance. Let me show you the pool variance. This is the pool variance, right? You need to first compute SP squared. That's a pool variance. And if you want to compute SP squared, N1 is a sample size chosen from group 1, and 2, the sample size chosen from group 2, okay? Now, when you have the sample size, chosen from, then the variance from each group is also given, okay? Now you can actually plug that in, and you're going to, so by the time you get that, then you find the square roots of that is going to be the SP. Okay, now you plug that in here, you plug all of that, but right now we're no longer going to check from the Z table. We're going to check from T table. Okay, and when we are checking from T table, don't forget the other time, checking from T table, we need degree of freedom, right? Now, because two populations are involved, this is what the degree of freedom. If I want to find the degree of freedom, it's going to be N1 plus N2 minus 2. How? Oh, I told you the other time, for one group, the degree of freedom is N minus 1. For another group, N minus 1, add them up. Okay, when you add them up, that's going to be N1 plus N2 minus 2. Does that make sense? Okay, that's going to be degree of freedom for that. Now, this is an example. We got this one from the textbook, the article, okay? And let me just tell you, they were talking about aquatic degradation, okay? Now, they said two independent, let me just, what we need. The first story is a background information giving, okay? Now, because this is actually published in the Journal of Environmental Pollution, okay, reports on an investigation undertaken in Cane Creek, Alabama, United States, to determine the relationship between the selected physiochemical parameters and different measures of micro invertebrate community structure. And one facet of the investigation was an evaluation of the effectiveness of a numerical species diversity index to indicate aquatic degradation due to acid mine drainage. Okay, and conceptually, a high index of micro invertebrate species diversity should indicate on stress aquatic system, while a low diversity index should. Okay, so giving that information now. Two independent sampling stations were chosen for this study, one located downstream from the acid mine discharge point and the other located upstream. Definitely they want to look at the effect of that acid on the stuff. That's why, it's like you are having two different stations. One is experimental, the other one is control. Does that make sense? Okay, now for 12 monthly samples, 12 monthly samples collected at the downstream station, the species diversity index has a mean value of 3.11, and the standard deviation of that, this mean and the standard deviation, they were from the sample. They computed that from the sample after 12 months of investigation, while the 10 monthly samples collected at the upstream station had a mean index value of that. You can see that, okay? If you take a look at this, they choose 12 sample from one station, 10 sample from another station. When you look at each of that, that is less than 30. Okay, now find a 90% confidence interval for the difference between the population mean for the two locations. Now I need you to listen now, assuming that the populations are approximately normally distributed with equal variances. Please pay attention. With equal variances. Because they say with equal variances, then you're actually going to use the idea of a pool variance. Because we use the idea of a pool variance whenever we are trying to construct a confidence interval for difference of means when the population variances are not given, but they are assumed to be equal. Does that make sense? That's what we're going to do here. Now, just like what I did the other time, you need to first find the difference of the means. Finding the difference of the mean, that's just going to give you a point estimate, right? That could be wrong or right. What is the next thing you're going to do? The next thing is to calculate the pool variance. Don't forget that. Okay, that's what I'm doing here. Okay, computing the pool variance. Okay, the pool variance is giving me 0.417. And after getting the pool variance, I need the square root of the pool variance, which is, which is what I'm getting here. Can you see that? You just take the square root of 0.417. That's going to give you that. Okay. Now, after that, what you just need, I want to set up the, just the formula now. Okay. Start plugging in. Okay. I'm start plugging in. I plug in the pool, what I get for the pool standard deviation, because the square root of a pool variance will give you pooled standard deviation. Okay, so that's what I put right here. Now, I actually need to go to table to check for T. Now, I need my degree of freedom. Don't forget N1 plus N2 minus 2, right? 12 plus 10 minus 2. That's going to be 20. So now I have my degree of freedom. I also need the level of significance, because if I want to check from T table, I need the degree of freedom and the level of significance. So how do I get my level of significance? I look at the level of confidence. The level of confidence is 90%. Of automatically, the level of significance will be 10%, because the level of significance is taking a level of error, level of statistical error. Now, if that is 10%, okay, 10% means 0.1, right? Now, if it is 0.1, that's why you see alpha equal 0.1. Okay, if alpha equal to 0.1, don't forget confidence interval is two-sided. Okay, you consider error to the left, error to the right. Because of that, you're going to divide this guy alpha by 2. 0.1 divided by 2, what does that give? 0.05. Now, if I want to check from T table now, I'm actually going to check at the level of significance of a 0.05 and the degree of freedom of 20. That will automatically give me 1.725. And I plug that in, and in the end, I got this result. In the end, we got this. Now we're telling the world the difference between that, the two locations now, line between 0.593 and 1.547. Now, how do we take decision here? If I want to take a decision here, whether the two locations are the same or not, whenever you are between a negative and a positive, you know what I mean? When you are between a negative and a positive, that means a zero lies, right? In the interval. Okay, when a zero lies in the interval, you know what that means? There is no significant difference in the means for the two locations. But right now, what is happening? This is from positive to positive. which means there exists a statistical significant difference between the locations, between the means of the two locations. Does that make sense now? That's how we interpret that. You know, how we advise that you also learn to interpret this. Okay? So that is that. Now, we want to go to the another one now. We are still on how to construct a confidence interval for difference of means. We now want to go into the third one. The third one, I want to construct confidence interval for difference of means, and the population variances are unknown, but they did not give us information whether the variances are going to be equal. Does that make sense? The second one we did, you know, the two population variances are unknown, but we were told, even though they are unknown, they are assuming them to be equal. But right now, when you take a look at what I'm talking about here, okay, the two variances, you know, they both unknown, and if they both unknown, okay, they are not equal. Even though they are unknown, they are not equal. And how am I going? What would be the formula to construct the confidence interval? It's actually going to be this guy. You see, this is the third formula I'm giving you today. This guy does not involve pooled variance. Okay, you see that? It's only sample variances and T that I'm going to check from the table. But I needed to pay attention. The way to get the degree of freedom here is highly complicated. This, let me show you. If I want to get a degree of freedom for this scenario, it's actually this guy. That is a formula to get the degree of freedom, you know, but do not be scared. This formula, okay, what do you just need? The sample variances, then and the sample sizes. You need 4 things in this formula. 4 things. The sample size from the first group, the sample size from the second group, the sample variance from the first group, the sample variance from the second group. This is what you're going to use to figure out your degree of freedom. Does that make sense? So this and the other one that we did, you are still checking from T table, but their degree of freedom will not be the same. The degree of freedom for the other one was N1 plus N2 minus 2, but this is what you're going to use to figure out the degree of freedom. Okay, now that is how that is done. Now I want to move to something else. The 3 scenarios that I described today, okay, they are for situation where the 2 groups that we want to compare are independent. Does that make sense? The 2 groups that we've been comparing, okay, they are for situation where they are independent. Does that make sense? What of in a situation where we got 2 groups that are dependent? How? How are they dependent? Then I'm going to tell you how they are dependent. For instance, let's say we are in a company now. Okay. Don't let me use company. Let me use what I used to do. Let's, for instance, when I teach, do you know why I used to give extra credit, right? I'm going to give you the story why I give extra credit. Because I know student will always they will want to do more, they will show more interest to be able to listen when they know there's a reward in focus. On average, that is the way we behave. Let's say, for instance, in this class, maybe I teach this class maybe before the midterm one, maybe I was not awarding extra credit, and maybe after midterm one exam I started awarding extra credit. Okay, and I want to compare your performance, okay, for the midterm one and the midterm two. Why is it dependent? Because it is the same is the same participant that I use in different occasions, except that I visited them in more than one occasion. Does that make sense? And when you have that kind of situation, that is what we call, dependent. Okay, they are dependent. They're going to be called paired observations. Does that make sense? They're going to be called paired observation because we're using the same participants. Okay, now how do we construct a confidence interval for the difference in that situation? Okay, in the situation where before, we normally call it before and after, like in medical line, where they are actually testing the effect of a particular drug. They look at maybe that drug is to reduce weight. They will look at your weight, before using the drug, and your weight after using the drug is the same individual, because we find it to the same individual. That make it a paired observations. Now, how do we construct the confidence interval for that kind of situation? Take a look at this. The formula that you are seeing now is actually the formula to do that. Okay, now, you know other ones that we've done, we normally call them difference of means. But this one, you know what it's called? Mean of the difference. Mean of the difference. Okay? Which means if I have 10 individuals, the first individual, okay, I'm going to have record before, record after. I subtract it. I'm going to do that across individuals. Then I'm now going to find the mean of the differences. That's what I call mean of the differences. Okay, so D bar is the mean of the differences. Then SD is the standard deviation of the differences. Does that make sense? We're still going to be checking from T table. Now, I'm going to show you an example now. Take a look at this. A study published in that. I don't want to waste my time. They want to look at the difference. Okay. The veteran, they're using 20 veteran in the same 20. Okay. They look at the TCD levels in plasma, and, TCD levels in fat tissue is the same person. Then they're going to find the difference, this minus that. Okay, they do it for all individuals. Can you see that DI, the difference could be negative or positive. Now, the way they are now, we're going to find the mean of that difference. We're going to find the standard deviation of the difference. Take a look at it. That's what we're doing here. Okay, so, getting that. This is the mean of the difference, D bar, the mean of the difference. This is the standard deviation of the difference. What are we going to do now? Then we're going to plug their mean into, if you come back here, this is the formula. You see the formula? We're going to plug that in, okay? And the degree of freedom here is n minus 1 for this. Always n minus 1. Does that make sense? It is not two group. It's the same group, except that they were visited in more than one occasion. Does that make sense? Okay, now, in the end, what do we get? It's between this and that. What does that mean? Oh my God. What does it mean? I have between negative and positive right now. Whenever you have between negative and positive, it means zero is in the interval. When the zero is in the interval, then you're trying to say there is no statistical difference between the two. Does that make sense? That is what we mean. Okay, I said from which we can conclude there is no significant difference between the mean TCD level in plasma and the mean TCD level in fat tissue. Don't forget, the TCD level in plasma and TCD level in fat tissue, they measure them from the same individuals. Does that make sense? Okay. Any question? I'm done with the means. I want to go into another parameter of interest that we call proportion. We use proportion when we are interested in a certain characteristics of interest, certain category within a population. Now, you know what I want to do? I'm going to give you the formula that we use to construct a confidence interval for proportion. Is this guy here. Okay? The Q cap is 1 minus P cap. Does that make sense? And this is another approach. But the second approach is waste your time. This is going to waste your time. So I'll prefer you use this one. Does that make sense? That's going to waste your time. Okay. Now we use, we normally focus on proportion when interest is on certain category within a population. Okay. Now let's take a look at an example now. Okay, in a random sample of N500 families owning television set in the city of Hamilton, Canada, it is found that S equal to 340 are subscribed to HBO. It is not everyone who watch a TV that subscribe to it. Out of 500 families now, 340 subscribe. That is the proportion. We're interested in those who subscribe. Now, find a 95% confidence interval for the actual proportion of families with television set in the city that subscribe to HBO. Now, if you want to use the formula, you need to first start from the point estimation. The point estimation is just going to be the number that subscribe over totality. That's going to give you 0.68. Okay, when that give you, let me tell you this. Whenever you are working with proportion, the confidence interval is always going to be, it's going to involve Z. It's always going to be Z. Okay, it's always going to be Z, the confidence interval for proportion. Does that make sense? Okay, so I just wanted to take note of that. Now, but we have a threshold. The condition here is NP must be greater or equal to 10 before I can use that. And N into 1 minus P must also greater or equal to 10. Okay, now, you know what I'm doing now? I'm plugging in the values into the formula. And for the Z, 95%, that will be 1.96. By the time you plug that in, you know what happened? Okay, this is the final answer now. Take a look at this. Now, do you know that this is going to make more sense than just this? Instead of you to say, 68% subscribe to the HBO, it doesn't make sense compared to when you say between 63 point something percent and 72 point something percent subscribe. This is more realistic because don't forget that this guy here is a random variable. If each and every one of you should conduct this study, you are not going to get the same as 0.68. And that is the reason why constructing the confidence interval will show us how sample reveal the overall view of the population, by you trying to incorporate what I call the margin of error. You consider error to the left and the error to the right. Okay, now I can say we are 95% confident that the true proportion we're looking for lies between that and that. Does that make sense? That is the end of the story for proportion for one group. Okay, what about proportion for two groups? We want to use the idea now to go to the proportion for two groups. Of course, I've already walked you through difference of means for two groups, comparing average GRE score before and after taking prep course. We've done all of that. But look at this. Compare the proportion of Minnesotans who own guns to the proportion of Wisconsinite who own guns. If you take a look at these are proportions. These are difference of proportions. Okay. Now, if you want to compare proportion, we're going to have a procedure. We're going to go into the two group, select sample randomly in your sample. How many in your sample possess that characteristics of interest? Okay. Now take a look at it now here. Population 1, population 2. Now, what are we looking for in the two population? These are true proportion. That's what we're looking for. But we don't have resources to study everybody in the population. What are we going to do? We're going to take a sample, right, from the two population. Then when we take a sample from the two population in each sample, we're going to count the number of successes. What do I mean by number of successes? The number of successes here means the number of the characteristics of interest. Like, okay, I'm talking about Minnesotans and Wisconsinite. Okay, I took a sample of Minnesotans. I took a sample of Wisconsinite, and X1 is going to be the number that own guns, the number of people that own guns in my sample. X2 is going to be the numbers of people that own guns in my sample from the Wisconsin. And you know what? I will be able to compute the sample proportions, which is just going to be X1 over N1 and X2 over, take a look at that. Okay, now there's a difference between this guy here. and this guy here. We got this guy from the sample. Why this is the true proportions we're looking for. The only way to get this guy is when we study everyone in the population. We do not have resources for that. Okay, now after doing that, now we now want to compare that. Okay, now what is the formula to use? We're going to start. What is the point estimate? This will be the point estimate, just subtracting P1, P cap, you've gotten this guy here, right? You've gotten this guy, right? Subtracting them, we only give you a single result, which could be wrong or right. Because of that, we needed to incorporate the confidence interval. And before you can actually construct a confidence interval, you need a standard error for the difference. Okay, now this is the mean. This is the standard deviation of the difference. If we're talking about proportion, okay, for single population, it's actually going to be it's only going to be square root of only this one. But when two populations are involved, I'm going to add another one. Does that make sense? You see now? Now, then I can be able to tell the world, the distribution is going to follow normal, provided the sample that we choose from the two groups are large. And how large is the large? Has to be at least story. And when that, and not only that, before I can use a formula for constructing difference of proportions, I have to investigate that N1, N1 multiplied by P cap 1 has to be at least 10, and N2 multiplied by P cap 2 also have to be at least 10, okay, and so on. So the moment that happens, we are ready. Now, let me take you there now. This is the formula. Do you see the formula? This is the formula for confidence interval of difference of proportion. Before you can use this formula, ensure this. Give me 1 second. You need to first investigate this guy. N1, N1 P cap 1 must be at least 10. N1 1 minus P cap 1 must be at least 10. N2, this must be at least 10. Then this must be at least 10. If there's a violation, okay, if there's a violation, you cannot proceed. That is a requirement. Does that make sense? Okay, now, okay, that's what I mean. Now, let's take a look at this example. The NCAA, oh, I love sport. I love sport. I love sport. Take a look at this now. The NCAA requires colleges to report the graduation rate of their athletes. In a sample of male and female student athletes, I know some students, I know some of my students, they do sports, they do sport. I love it, Okay, now 43 of the 53 females surveyed are graduated. Okay, whereas 58 of the 102 male are graduated. Calculate and interpret the 99% confidence interval for the difference in the true proportion of female athletes who graduate and the male athlete who graduate. That's what we want to see. But before you start, 4 of us investigate this. When this guy old, then go ahead and figure out the point estimate for female and the point estimate for male, okay, which is this, 43 out of 53 for that, 58 out of that, and after getting this, you are ready for confidence interval. Now, this is the formula now. You see the formula now, okay? Why Z 0.005? Because they say 99, alpha will be 1%. 1% means 0.01, right? 0.01 divided by 2, that would be 0.005. When you check that guy from table, that would be 2.575. Then start plugging in the values for the P cap. You've already obtained all of that before. Take a look at this guy. You've obtained, you see, 0.811, 0.56, you just start plugging them in. Okay. When you plug them in the hand, we got this. Now, is there a statistical significant difference between male athlete and female athlete who graduate? There is, because this does not contain zero. Does that make sense? I told you when you go from negative to positive, okay, that includes zero. Now let me tell you this. You're going to report statistical significant difference when you have positive to positive or negative to negative. Does that make sense? Positive to positive does not contain zero. Negative to negative does not contain zero. The only one that contains zero is negative to positive. Okay, right now, so I'm going to say, look at the way we're going to interpret this now. I need you to pay attention. For those of you who will be presenting maybe this may look like your area. Some of you may want to work with a confidence interval of the difference. Of course, if you have this now and you want to interpret, you're going to say, we are 99% confident that the true proportion of female student athletes that graduate is between that and that, higher than. Why do I say higher than? Positive to positive indicate higher down. Negative to negative indicate lower down. Does that make sense? Okay, that's what we mean. Any question on that? Any question? Any question? Okay, the next 10 minutes, we're going to talk about the method of estimation. When we have a distribution and we want to estimate parameter in the distribution, we have a method that we use. Okay, method of maximum likelihood is one of the most popular method. The method of maximum likelihood is actually using the knowledge of independence that we've done before. Okay, requires that we should get the likelihood function. If I have a distribution f of st, then I can just get the product of the distribution. Okay, f of x1 theta, f of s2 theta, and out to f of xn. Why am I doing that? Because x1, x2 up to xn are independent. I told you the other time, when x1 x2 up to xn are independent, what does that mean? The probability of the joint occurrence will be equal to what? The product of the respective so the likelihood is the same thing as the probability of the joint occurrence of the event. Okay, now we want to visit a distribution now. Please pay attention. This is technical. This is theoretical. Now, take a look at this distribution. This is a Poisson distribution. We use this to model real event. And maybe we actually, the parameter is mu. We want to use the method of maximum likelihood to derive what the formula is going to be for the mu. What are we going to do? We need to write it. This is a likelihood of a Poisson. You know what likelihood mean? Like writing that in n term. You see, exponential is power minus mu become what? Under this is product sign. Okay, like product sign. This is going to carry, you can see here, n instead of just that. Then whenever something carrying s, there's going to be that thing raised to power summation s. You know why? Because this is what you are having. You are having this. What is going to happen by law of it? You're going to write just one and add up the exponent, right? And that was why that guy was mu summation s. But when you take a look at s factorial in n term, it's just going to be product s factorial. Now, what I have here is a likelihood function. Now, because likelihood function, if you take a look at likelihood function, it's multiplicative, differentiate, because we want to use a method of, when I talk about maximum likelihood, I'm actually looking for the value of the parameter mu that will maximize the likelihood. It means I'm actually going to seek redress in optimization, okay, which means I want to optimize this, and optimizing multiplicative model could be complicated. What I'm going to do is to introduce a log. Okay, what am I doing here? I'm introducing a log. When I introduce a log, what has happened? log of all of this, okay? And it's going to be a natural log. Natural log of that is going to be minus mu. Natural log of this is going to be that, log of this is going to come down summation s log of mu. Then log of this, okay, because it's in the denominator, it's going to be negative log of that. We're applying the law of logarithm in math. Now, when you take a look at this guy now, this is called log of the maximum likelihood. We're taking the log because it will be very easy to maximize the log of the likelihood compared to the likelihood, and it is mathematically proved and statistically observed when I optimize likelihood and I optimize the log of the likelihood, they give the same result. Okay, and why is it that we can't do likelihood directly? Because it's going to be complicated. Now you now know what I'm going to do now. I will differentiate with respect to mu. Okay, differentiating this will be very easy. With respect to mu, I'm going to have that, have this, this is going to be 0. Now, when I have this, you know what I'm going to do? I will set it to 0. I'm actually going to set this to 0. When I set this to 0, what do I want to find? I want to find mu. Now my mu is going to give me that, which is going to be mu cap. I'm going to put a cap. It's going to be x bar, which means if I want to figure out the mu, the parameter in the distribution, I only need to find the average of my data set. This becomes the maximum likelihood estimator. Okay. Now, I'm not going to walk you through this one. Is going to be more complicated. If you want to take more, this is for the mean, for the normal. What I want, this one is for the normal, but you don't need it. Okay, you don't need it. When you come back for highly theoretical statistics, then you're going to do that. But let me give you an example on what we just did. Take a look at it. Suppose 10 rats are used in a biomedical study where they are injected with cancer cells and then given a cancer drug that is designed to increase their survival rates. The survival times in months are given as this. And they said, assuming that the exponential distribution applies. You remember why is exponential distribution applies? I told you the other time, exponential distribution is used to model waiting time before the occurrence of an event. Survival time is this, is that. Does that make sense? Now, this is the exponential, right? When I have a distribution like this, I need parameter beta. You know what you're going to do? You can use the method of maximum likelihood. 4 of us write this in a likelihood form. Then take the log. This is taking the log, right? After taking the log, differentiate with respect to beta. Set it to 0. That give you x. This guy give you s bar. When that give you s bar, what are you going to do? If that give you x bar, then if the beta give you x bar, then you're going to go to the data. You find the average of this. Okay, the average of this data is the same thing as a beta cap. It's 16.2. I'm done. Okay. Now, finally, let me see. The theta link. Let me see. This is a different one. I think I'm going to leave you with this one. Is there any question today? Now, out of an exam, I bring a different distribution, right? I bring a different distribution. Before of us get the maximum likelihood, I give you data, okay? It is not all the time that it's going to be X bar. At time, it could be something else. I was doing this. I was doing something here, and my theta cap gave this. This is going to come from gamma. Here, I'm assuming gamma. Okay, I use a gamma density. I arrive at this. In this situation where I have n over this now, okay, in my data, you know what I'm going to do to my data? I'm going to do lean of each of the data, add them up. Then the number of ops that is going to be that, which is going to be a likelihood. But if I'm going to bring this in exam, of course, this will be part of my practice question. This is where I'm going to stop today. Oh, 109. Good job. I think I planned this on time. So the material for tomorrow, I'm sorry,